having representatives for Disruptive Materials Group talk to us about upsized drug delivery and other applications. Welcome.
Good morning, guys. So we're the group that went on a company visit to Disruptive Materials. They are making this very fascinating compound called ipsalites, and we're going to talk about drug delivery and other applications that can be used with ipsalites. I'm Kjartan, Anton, and Leonie. I'll start by talking about ipsalite and drug delivery. Anton will tell you how it's made and some other stuff, and then Leonie will finish up with antibacterial effects and further applications. Okay, let's start. What is ipsalite? Ipsalite is the best material in the world. It was discovered here in Uppsala in 2013. It's a magnesium carbonate that is ultra absorbing. It has a very large surface area, and as you will see, it has some very interesting biotechnological properties. Let's define drug delivery. Drug delivery is a method or process of bringing an active pharmaceutical ingredient into the human body or animals. And this can be done in many different ways. You can take tablets, you can put something on your skin, or you can inject yourself. But what we're interested in is the per-oral use, the tablets. Ipsalite is a nanoparticle. There are many nanoparticles currently being developed as drug delivery systems. I won't go through all of them, but there are 5 groups, and we're interested in the porous materials. Porous materials are solid materials that have pores in them, and they make up this matrix. Before I tell you more about porous materials, it's important to know the difference between the crystalline states and the amorphous state of drugs. So imagine that these are pills, and this one over here is this crystalline state is highly ordered and very stable. So if you take a drug in this form, it would most likely be a tablet that you swallowed, and then it would slowly dissociate in the gut. And then you have the amorphous state. It's highly unordered. It's not as stable, and it takes less energy for the atoms to break off each other. So, and it's highly desirable to have this as a drug, but the downside is it's not stable. So if you just take this and try to swallow it, it would probably just dissolve in your mouth. So we need something to shield the drug, and for that ipsalite can be used. Ipsalite can serve as like a vessel, and the pores are filled with the drug molecules. They're put in here, and this makes it a stable long-term storage for the drugs. And you can take a pill, and the drug molecules are in this amorphous state. They can fall off pretty easily. You swallow it, and it dissociates at the right place. So just to sum up what ipsalite can do in drug delivery, it can provide a fast and predictable drug release. It can improve the dissolution with tunable pores, and that causes an increased bioavailability of drugs. And now Anton will tell us about his part.
Thank you. This way.
Does this work? Yeah? Can I borrow? No, never mind. There it is. Okay, so I'll be talking a bit more about the properties of porous materials that make them so effective as drug delivery vehicles. And in particular, I'll be talking about the thing. Is this all right? Yeah? All right. It's working, yeah. Hey, focus on this, not on me, all right? Okay, so I'll be talking about Upsolite and the properties that makes it so valuable as a drug delivery vehicle. And first of all, I'll be talking about what I'd call the dilemma of new APIs. And an API stands for an active pharmaceutical ingredient, or in easier terms, a newly developed drug. So the thing is that about 30% of all newly developed drugs today have high aqueous solubility, which means that in the gut it will probably have high absorption, because the high solubility in water equals that it's able to be taken up in the intestine. However, about 70% of the newly synthesized drugs have low aqueous solubility, which means that its probability will be very low, and probably too low to actually be able to be effectively used. So this means that many new pharmaceutical drugs are basically, they are canned from the start because they can't be delivered efficiently. Here we can use Upsolite as a drug delivery vehicle. And if you pack the drug into Upsolite, it will be packed in an amorphous form. And as previously mentioned, an amorphous form have a higher rate of dissolution than the crystalline form of a drug. And a crystalline form of the drug is what you'll usually take when you take a drug in a pill, or as usual today. So you would probably want to take a drug with low aqueous solubility and put it into and load it onto Upsolite to increase its dissolution rate and its absorption rate. So the thing is that Upsolite is covered by all of these pores, or these crevices, and when you load a drug into Upsolite, they all move into these pores, and they stay there. And only weak interactions are used, so we're talking about van der Waals forces and stuff like that. There are no chemical bonding, such as covalent bonds, which is why these drugs that are packed into the material both pack easily and dissolve easily. Since the material is covered by pores, the surface area is pretty big. In many cases, we're talking about 500 square meters per gram of Upsolite material, which is a lot. So obviously, a lot of the drug in question can be stored inside of the pores, as well as on the outside, in a lot of cases. However, in the case of Upsolite, the material does not get stored outside of the particle, but only inside of the pores. So when the drug is released inside the gut, in a theoretical scenario, the release kinetics can be tuned based on the size of the Upsolite particle and the pore size of the Upsolite particle. These can all be decided during manufacturing. So you could, for an example, decide the size of the particle by crushing it and sieving it into the desired size. You could change the size of the pores by modifying the temperature used during the manufacturing process. And what this actually does is that it increases or decreases the rate of dissolution from the material out into the environment outside. So, for an example, when you increase the pore size of the drug, of the Upsolite particle, the drug will be increasingly exposed to the environment and will increase the dissolution rate. There are also some issues with increasing or decreasing the pore size of Upsolite. Ideally, you would like to have such a large pore size as possible, but since that increases the dissolution rate in a lot of cases. But in this case, for the drug itraconazole, increasing the pore size actually prompts crystallization inside of the pores. And as a reminder, we do not want crystallization because that removes the whole point of this. Because when the drug is normally loaded into the pores, it is in an amorphous state, and that is what you want because that is what increases the solubility of an already weakly soluble drug. There has been numerous studies of different drugs that have been attempted to load into upsolites and check their dissolution rates compared to the crystalline version of it. In this case, we got celecoxib, we got cinnarizine, and we got griseofulvine. These are three particles with very different properties, both in terms of chemical structure and in terms of their one of them is acidic, one of them is slightly basic, and one of them is neutral, as it is non-proteolytic within the body. They also have ranging aqueous solubility values. This one is the highest, and this one is the lowest, but all of these three are very low, and in general they are very inefficient when they are taken by the traditional oral pathway. However, if you load them into upsolite, and in this case, all three of them were loaded into upsolite particles with an average pore area coverage of 55%. You get this. And this is why upsolite is so important right now, and this is why you should be interested in it when it comes to drug loading. Because compared to the crystallized version, which is what we would usually take, taking the drug in an amorphous form yields a 5 times higher dissolution rate, 3 times higher, and 2 times higher. So it's positive dissolution rates compared to the crystalline version across the board. If you would compare this to, also considering that all of these three have very varying properties, it would seem that upsolite is a pretty neutral material that can be used for a wide array of drugs as well. There have still not been any clinical studies, but seeing this, it is probably expected that this would lead to a way higher bioavailability in the body compared to the methods of drug delivery that exist today.
All right. So now the cool thing is that we can not only use upsolite for drug delivery, but it also has a lot of other applications as well. And I'm going to be talking about one of those, or two of those actually. So let's start off with the antibiotic effect of upsolite. And because one of the problems with the whole assessment of this new material is that the only research has been done by the company itself, which is kind of biased because, of course, they want to sell it. You know, they're making profit off of it. But so a study was conducted, and they chose a model organism, Staphylococcus epidermis, which is a bacteria found on normal skin, on healthy human skin. And they mixed it with upsolite and other comparable magnesium or silica porous materials that are being used today. And it was, they mixed a reducing dye or a reporter dye called resatsurine into it. And if the cells were continuing to be metabolically active and healthy, then they would reduce the dye, which makes it turn purple, as we can see here, and that's fluorescent, and that can be quantified. And so you can really see it can be coupled between how alive they are and how purple this thing is. And so MMC stands for mesoporous magnesium carbonate, which is upsolite. And the yellow here is the negative control. And in most of the studies, it's always being compared to SBA 15, which is silica. And that's the material that is being used today in cosmetics as a mesoporous material, and that's like the main competition of upsolite. So the goal is always to show we're so much better. So as you can see, SBA 15, after 3 hours, they had a viability reduction of 70%, And MMC is basically a flatliner. It's hard to see now, but it's just to show that this was it has a 100% bacteriostatic effect. Why bacteriostatic? Because they did a recovery test afterwards, and the cells regain their viability after a certain time. But they regained it faster with SBA 15, meaning that oopsolite is better, just as a side note. So there's the scientific community. They're not really sure about what causes this antibiotic effect. And these are the 3 potential candidates that they have in mind. So for one, it's the pH alkaline effect. That model bacteria has an optimum at 7.5 and loses its viability at 10.5. But in the test, or in that curve I just showed you, it was already at 0 at a pH of 8.5. So that cannot have been the sole cause. And another main suspect was therefore the formation of ROS, which means reactive oxygen species. And it's basically like similar to the concept of free radicals, and they attack the peptide bonds in the cell membrane, and that leads to a loss of integrity of the cell membrane, which works very similar to what known antibiotics do today. And because oopsolite is so cool, it's not only antibiotic effects, but you can also use it for all these things on the mind map. I don't have enough time to walk you through everything, but the main aspect or advantage of oopsolite for all these other applications is that it can take up an insane quantity of humidity up from its environment, even if the humidity, it doesn't have to be like 100% to, be taken up. It can, even at a low room moisture, oopsolite can take up a lot of humidity. And so you can use that to shield electronic devices from moisture. For example, in those really nice new TVs, the OLEDs, they have to be shielded from moisture, and that enhances their lifespan. Oopsolite can absorb heavy metals into the pores, so you can use it for like environmental toxic spills to clean up pollution, just like a sponge that soaks up all your poisonous stuff. You can also use it like for the classical moisture absorption in food or in dishwashers, if you guys are interested in that. And there's already a company producing climbing chalk with oopsolite in it because, climbers sweat a lot on their palms, and the company Black Diamond, I don't know if someone climbs here, but they are producing climbing chalk that already contains this product. And it won Best Gear 2018 a few weeks ago, so really cool. And then for dermatology and cosmetics, did I already say it absorbs UV? No, it absorbs UV radiation. So you can use it as a sunscreen, and at the same time, it can absorb the sebum on your face. So it like mattifying powder, dry shampoo, baby powder, all of those potential applications. So to wrap up, oopsolite is very, very potent for drug delivery. We can make all those drugs that are being lost in the pipeline because they're not soluble. As of now, we can regain those and actually start using those potential therapeutics. And we can also use it for a lot of other things as well. And we think the company has a lot of potential, and we're really excited to see where it goes. Thank you very much.
Let's thank the group for their presentation, and let's also praise them for finding the world's smallest pointer to go with the world's smallest screen. Well done. Questions from the audience?
I don't know if I missed it, but what happens to oopsolite once it goes to the digestive system?
I can answer that.
Yeah, sure.
Okay. So the drug is taken up, but oopsolite is too big to be absorbed, so it just leaves the body.
Okay.
So
And it's not polluting the environment anymore.
no, it's just a magnesium carbonate, so it's an alkali metal, and
So they've only conducted one study on that yet, but they were testing it on toxicity on skin and intravenously in mice, and so far so good. So there were no irritations whatsoever. Um, everything was fine, but it's always hard to say because it's exactly one study. You don't have any other data on it yet.
But I can add to that. The reason why many things are toxic is because they enter the bloodstream. For example, liposomes, they can be absorbed into fatty tissue. And I think it's a very important aspect of it, so it never enters the bloodstream. It's always outside the body.
Outside the bloodstream.
Outside the bloodstream.
Joe, you had a question? Yeah.
It was answered, thank you.
Can you go back to the graph where you compared raw materials?
About to which
One more,
aspect?
one more.
Yeah.
How does the fluorescence indicate that the reactivity?
Because the that dye is the dye is reduced by enzymes that are only active if the bacteria is still viable. So if the dye isn't being reduced, then there's no pink blood vessels being created. So it's not reduced if the organism isn't doing something.
Why do you compare it to silica though? Or isn't silica used as an antibiotic?
No, but it's like silica is like the main competitor. For example, so they're working, or we suspect they were very secretive about information, but we suspect that they're working on facial powders. And if you buy a Maybelline facial powder, that has the silica in it. So at the same time, silica absorbs that like excess sebum on your face as well. But at the same time, they say if you, for example, like acne is caused by having like infections in your pores. So if you would have something antibiotic on top of that, like that absorbs your moisture and is antibiotic or like keeps your infections down, that would be a double win-win. And since they are trying to, gain that market share that is now SPA 15 or silicas, they need to come in and say we're a lot better. So that's why they're comparing, but silica themselves, they don't advertise them.
So it's not that it's used to cause an antibiotic.
No. It's just like a nice little extra, but it's not.
Silica is also being used for drug delivery, but the main difference from extravased silica is that you can't tune the pore size of silica, but you can in Ipsolite, so it has like so much more potential.
Now, so it doesn't actually have an antibiotic effect. It just creates a hostile environment for bacteria. Like, I mean, when I think of antibiotics,
It doesn't kill it
But it's
because
also-
It's bacteriostatic. I mean, like,
so it just creates an environment that's not friendly for bacteria.
well, I mean, depends on your definition of antibiotic, but like all antibiotics that are bacteriostatic would do that per definition as well, wouldn't it?
I think it's sorry, I would think about that because of the synthesis of a.
Well, I mean, the
They might have definition is wrong.
looks like it also tampers with the cell membrane of bacteria. So that is not it's not just the hostile environment of being like the pH is not being optimal. It actually physically interacts with the cell membrane and causes disruption there.
I thought you said that was because it was oxidative.
Well, yes, but those reactive oxygen species are formed on the surface of moving materials. So they're not just swimming around. They do have this type.
Anton, you said that Ipsolite was not of other particles on the surface, only in the core.
Yeah.
Why is that important?
Well, I'd say that the main thing, well, apart from making a point out of it, because the picture is not right, but other than that, as far as we know, as far as I know, it has been hard to see, like, the amorphous formations of drugs, they are formed inside of the pores, but not outside of them for some reason. And that's a very important point to make, because otherwise it wouldn't make sense on the picture. Yeah, and yeah.